Welcome to This Explainer. Today, we're diving into the journey of a learner, looking at how AI actually works under the hood. And, despite all the buzzwords out there, AI doesn't possess some mysterious hidden intelligence. Spoiler alert, it absolutely isn't magic. It's actually a fascinating, highly structured process. So let's look under the hood and see how a machine truly learns. Let's kick things off with a little thought experiment. Imagine your math professor announces a final exam, but on test day, they hand you the exact same practice questions you solved the night before. Now, we've all dreamed of this happening, right? But would that test actually measure your true mathematical ability? Probably not. You'd totally ace it just by memorizing the answers. A valid exam actually needs completely unseen questions. And that brilliantly illustrates the core tension in machine learning. You see, an intelligent system shouldn't just memorize historical data. Its true holy grail is something called generalization, which just means handling completely new, unseen situations. Like, a bank needs a system to catch brand new fraud tactics, not just yesterday's scams. Without generalization, a model is practically useless.
All right, that brings us to our first section, splitting the data.
To ensure these systems are actually generalizing and not just cheating on the test, responsible machine learning researchers have to be pretty ruthless with their data. Because if an algorithm sees everything, it might achieve perfect accuracy in the lab, but completely collapse in the real world. So they divide the data up. A really common split is 70% for training, 15% for validation, and keeping a final 15% locked completely away for testing. Now, what's totally fascinating here is how exactly this mirrors human learning. Think about it. The training data set, that acts as the textbook. The validation data set acts as a mock exam. It lets researchers tweak the model and adjust study methods without touching the final test. And finally, the testing data is the actual final exam. Success on those entirely unseen questions is our only proof of genuine generalization. Moving right along to section 2, what is a model? You hear the word model literally all the time in the news. But beyond the hype, what is it exactly? It's actually remarkably elegant. It's not some complex physical box or just a massive folder of stored files. A machine learning model is simply a mathematical summary of everything the algorithm has learned. It's a mathematical representation of patterns and relationships extracted from data. So the crucial takeaway here is that data is not the model. Imagine a doctor reading 100 medical textbooks. The books are the raw data, but the medical knowledge that ends up extracted into the doctor's brain, that is the model. This is exactly why you can download a really powerful AI right to your phone. You're downloading the extracted mathematical relationships. You're not downloading the terabytes of raw internet data it studied. The original data can often just be left behind.
Which brings us to section 3, learning by adjusting.
So how exactly is this knowledge extracted? Well, let's look at a real-world example. If we wanted an AI to predict dangerous PM 2.5 air pollution, say from a wildfire, we'd feed it a bunch of historical inputs, variables like burned area, temperature, wind speed, humidity, and so on. But here's the thing. Initially, the AI is completely clueless. Its very first prediction for pollution levels is entirely random. But this is where parameters come in. Think of them like the ingredients in a cake recipe. If the cake is too dry, you add milk. Too sweet, you cut the sugar. The algorithm continually tweaks these mathematical settings, the parameters, after every single random guess. The parameters are the ingredients, and after millions of micro-adjustments, the final perfected recipe is your model. And the incredible part about all of this, no human programmer ever hard-coded rigid rules. Nobody sat down and typed, if wind speed is this and humidity is 70%, increase pollution by 12. No way. The algorithm discovers these complex relationships entirely on its own. The apparent intelligence simply emerges from millions of mathematical parameter adjustments happening at an extraordinary scale. Now, on to section 4, the power of mistakes. So what is the secret engine actually driving all of these brilliant adjustments? It's something you might not expect. Making mistakes. Imagine a child learning to shoot a basketball. If they miss a throw, they don't need a physics lecture, right? They naturally adjust their next throw based entirely on that mistake. Well, for an AI model, it's the exact same concept. It absolutely requires mistakes to provide direction and move closer to perfection. Let's go back to our wildfire model for a second.
If the model guesses a pollution level of 18, but the actual real-world sensor reads 47, it just subtracts the two to discover an error of exactly 29 micrograms per cubic meter. The model now knows precisely how wrong it was. To keep track of all these mistakes, computers use a brilliant tool called a loss function. You can think of it as the ultimate strict teacher grading homework. Instead of just marking an answer incorrect, it gives a clear numerical score indicating exactly how badly the model performed. This loss function becomes the model's compass, constantly guiding the learning algorithm toward a better solution. For predicting numbers, models often use something called mean squared error. The steps are pretty straightforward. You calculate the error, square it, and then calculate the average. But why square it? Well, two big reasons. First, it removes negative signs so mistakes don't just cancel each other out. But more importantly, it exponentially punishes huge blunders. An error of 2 becomes 4, but an error of 20 becomes 400. It literally forces the algorithm to pay huge attention to fixing its largest mistakes. Now, of course, different problems require completely different mathematical tools. Mean squared error is great for regression, predicting numbers like temperature or pollution. But predicting if a medical x-ray shows pneumonia versus no pneumonia, that's a classification task. It's simply correct or incorrect. And that requires entirely different loss functions like cross-entropy. But honestly, the core goal is always the exact same, measuring how far off the prediction was. Ultimately, no matter the specific math, a loss function is just like your car's GPS. It continuously compares your current location, which is the prediction, to your final destination, the correct answer. If you turn down the wrong street, the system instantly measures how far off track you are, and it forces a route recalculation closer to the correct answer until you arrive safely. But this leaves us with a really fascinating, provocative question. The loss function graded the prediction, right? So the model knows it made a massive mistake. But how does it actually know which way to adjust its thousands of parameters? Should it increase one, decrease another? How does it actually know what mathematical direction leads toward a better prediction? Well, that puzzle is solved by a stunning mathematical optimization process called gradient descent. It's kind of like blindly finding your way down a foggy mountain by just feeling for the steepest step downward. But we will have to explore that incredible journey in our next explainer. Until then, think about this. If intelligence is just math continuously adjusting itself through mistakes, how many mistakes does it take to learn something truly profound? Thanks so much for watching, and we'll catch you next time.